Okay, so we've looked at Pascal's triangle, and of course we can see that we develop a pattern. Pascal's triangle shows us that there is a pattern that exists when we are raising binomials to a given power, to a certain power. And we're going to expand upon that in this particular lesson by looking at something called the binomial theorem. Because if we were to sit there and write out that Pascal's triangle over and over again, it'd get kind of laborious and boring. But before we actually move to the binomial theorem, I just want to kind of get an idea of maybe what is going on and why we might want to use it. So let's say that we've got a binomial here, and I've got x plus y. I'm going to say raised to the, in this example, fourth power for this. Well, if we were to multiply that out by hand or raise that by hand, we would actually be doing this. We'd go x plus y times x plus y times x plus y times x plus y. And we could use FOIL. We could FOIL those two terms. And let's see. Well, let's just do that. We get x times x is x squared plus xy plus, it's going to FOIL this. Now coming in here, y plus y times x. Well, that's just xy if I rewrite it that way. And then y times y, y squared, and that would equal x squared plus 2xy plus y squared. But then I'd have to take that and FOIL it against x plus y again. And as you can see, this is going to get pretty heavy duty stuff because it's technically x plus y. Well, I could end up here with x squared. Since x plus y equals this, well, then this would also equal that. And I could have x squared plus 2xy, well, xy, plus y squared times x squared plus 2xy plus y squared. And I could sit there and FOIL that trinomial, but it would really get to become a really large pain. So, and what if I had x plus y to the 10th, which is like the guided practice example on page 700 in example 2, says expand x plus y to the 10th. Well, I mean, I'd be all day foiling. And so this is where we can use the binomial theorem. So we're going to move to the next slide, and we're going to take a couple of slides and break down this binomial theorem by hand. And then we're going to end up looking how we can use our calculator to give us the binomial coefficients without trying to go all the way through a Pascal's triangle, several layers, and so on and so forth. But let's skip over here to the next slide, and we'll break down, I guess is what I'm going to say, this binomial theorem that we're getting ready to look at. All right, so here you see on the top of the screen this binomial theorem, and it says here, if n, I'm reading right here for right now, if n is a natural number, then a plus n raised to the power of n equals all this mess right here, which then equals the summation of n sigma k equals 0, and then we got n factorial over k factorial, parentheses n minus k factorial, and then we've got a n minus k, pk, bk. Okay, that's pretty confusing looking. Now, this portion right here, I'm going to focus just on this portion right here of this binomial theorem. A raised to the power of n minus k, bk. Now, what that's giving us what, if I'm expanding a binomial, that's going to tell me what the exponent values are of my variables as I expand that binomial. So, let's say I've got a binomial x, well, maybe I ought to use a for this. So I got a plus b raised to the 5th power. And the only thing I'm going to focus on right now, let me just say, this portion of the binomial theorem is going to give me the lead coefficients, or give me the binomial coefficients, but I'm not going to focus on that right now. I'm going to focus on that on the next slide. So I've got a plus b raised to the 5th power, and I want to draw my attention to this portion of this binomial theorem, is what's happening to the powers of the variables. Now, in this case, n is equal to 5, because we're raising it to the 5th power. So you can see right here and right here. Okay, so if I go through that, then I'm going to have a to the 5th power plus, and I'm leaving some space because there will be some binomial coefficients coming in here later. Well, I've got a raised to the power of n minus k. Well, I start off at k is equal to 0, which is what I've got right here, and I just end up with a to the 5th power. Now, my second term, when k is equal to 1, I've got a to the 4th power b. So I plug in n for k, 5 for n, 1 for k. N minus k is 5 minus 1 is equal to 4, and then b is raised to the 1st power. Now, when k is 2, well, I got a raised to the power of 5 minus 2, so that's a cubed, and b squared. Remember, I'm going up I'm taking k from 0 up to 5. All right, my next term. Well, this time a k is equal to 3. Well, 5 minus 3 is 2, so a is going to be raised to the 2nd power, a squared, and b is cubed, plus. Well, when k is 4, well, 5 minus 4 is 1, so I've got a, and then b, k is 4, so b is now raised to the 4th power, and then plus. When k is 5, well, I got 5 minus 5 is 0. Well, anything raised to the 0 power is just 1, so I'm just not going to write it, and then I'm left with b to the 5th power. Now, notice the pattern here. My first variable, my a, we start off with it raised to the power that we are expanding the binomial to. And you can see that these values of a start at 5 and go all the way down, 5, 4, 3, 2, 1. And finally here, this is a to the 0, or just 1. Now, what's happening with my second variable? Well, it's doing the opposite. It starts off at b to the 0 power. Let's say that's b to the 0 power, and that just equals 1. And then it's going up, so now it's b to the 1st power. Starts at b to the 0, then it goes b to the 1st, b to the 2nd, b to the 3rd, b to the 4th, and then finally ends at b to the 5th, which is what we're expanding this binomial to. Now, one other pattern is existing. If I look at the powers of the two variables in each of these expressions, well, here I got 5 plus 0, well, that equals 5. And here I got 4 plus 1, that equals 5. And 3 plus 2, that equals 5. 2 plus 3 equals 5. 1 plus 4 equals 5. And finally, I end up with just b to the 5th. So, And each of the expressions, as I'm expanding this binomial, the exponential powers have to equal what I am expanding the binomial to. In this case, it's 5. So 5 plus 0 is 5, 4 plus 1 is 5, 3 2 is 5, 2 3 is 5, 1 4 is 5, and finally 5. Now that's what's happening with the variable. And then the next slide here, we're going to look at what's happening with the binomial coefficient. Okay, in this section, or in this slide, I'm going to put my primary focus here on this binomial theorem on this portion right here, which gives us, we can use to calculate the binomial coefficient of the expanded binomial. Now, honestly, the only reason why I'm doing this is because this is for those that may not have a graphing calculator and are having to do it by hand. Otherwise, I would skip this altogether and go right straight to the calculator. And let me say this, I've said this before, if you do not have a graphing calculator, you need to get one. Your life is going to be considerably more difficult in this math course without it. Now, you can, I'm going to suggest that if you have a TI-83, that's good, that's fine. There will be occasions on a TI-83 that it doesn't function exactly like a TI-84, and my help for you may be a little bit limited, but take heart. YouTube, if you go to YouTube and search for just about anything on a TI-83, you're going to find how to do it. TI-84, if you're buying a new calculator, I'm going to suggest that that's probably the first choice, is to buy a TI-84. It's the one that I'm most familiar with. And, well, I just give you that choice. Now, there are phone applications, phone emulators, and they can work, certainly so. I will tell you that I'm not going to be familiar with every phone emulator. You would have, in many cases, you're going to have to use your own resourcefulness to figure out how to do things, but you can get by with a phone emulator. Now, I have bought a TI-NI Inspire that I'm learning how to use, and if you really wanted to step up, and it's a very nice, very fancy calculator, I would even suggest that one, but my primary would be the TI-84. Anything else, whether it's a phone emulator or a TI-83, we may run into occasions that I may not know exactly how to help you. But that being the case, we're going to look at this portion of the binomial theorem that allows us to calculate the binomial coefficient. Now, because it is laborious and difficult to use, I'm only in this example, let's say that we've got a binomial a plus b raised to the third power. Now, so in this case, n is equal to 3. We start off with k equal to 0, and then we're going to work our way up to 3. K equals 0, k equal 1, k equal 2. So we have this factorial formula where for the first term, I would have 3 factorial over k is equal to 0, 0 factorial times n, in this case I should say 3, n is 3, minus 0 factorial. Okay? All right. Now, that's going to equal 3 factorial over 0 factorial, 3 factorial. Now, by definition, by rule, 3 factorial is equal to 1. So I got 1 times 3 factorial. Well, 3 factorial times 3 factorial is just going to equal 1. All right, so we would then have a cubed as our first term. All right, now, what if k is 1? Well, I've still got 3 factorial over 1 factorial, 3 minus 3 minus 1 factorial. That equals 3 factorial over, well, 1 factorial is also just equal to 1, and 2 factorial. Okay, now 3 factorial is 3 times 2 times 1. 1, and then 2 factorial is 2 times 1. Well, the 2 times 1 is going to cancel, and I'm going to be left with 3. All right, so over here I'm going to have 3a squared b. All right, now what about when k is 2? Well, I got 3 factorial over 2 factorial over 3 minus 2 factorial. So then I've got 3 factorial times 2 factorial times 1 factorial. And that's going to give me 3 factorial over, well, 1 factorial is just 1, so 2 factorial. And again, I've got 3 times 2 times 1, that's 3 factorial, times 2 times 1. 2 times 1 are going to cancel, and I've got 3. And now I've got plus 3ab squared. And lastly, I'm going to be running close to out of room. I'm going to take it back up here. So now k is equal to 3, so I got 3 factorial over 3 factorial, 3 minus 3 factorial, and that equals 3 factorial over 3 factorial. Well, 3 minus 3, 0 factorial is just equal to 1, and so I end up with 3 factorial over 3 factorial, and that equals 1. And so I've got plus b, q. All right, so there we see the pattern. One, I've got a pattern there, a symmetrical pattern in my binomial coefficients, 1, 3, 3, 1. I can see that my exponents, I got a cubed, and then I got a squared, b squared. Well, 2 and 1 is 3. I got a, b squared. Well, 1 and 2 is 3, and then b cubed, 3, and there we go. So that focuses on this portion and builds into this portion. All right, now we're going to go and we're going to look how we could write this as a combinatoric equation, which is going to then lead us to the calculator. All right, so in this example, I'm actually going to take a look at this portion of what I've got. Okay, now if I notice here, I can see that I got combinatorics. I got NCO, like there. I got NC1, and so on down the line. So let's look at how we could rewrite this as a combinatorics, and then we'll move to the calculator. So let's say this time I got, well, I'll stick with a plus b, let's say raised to the 5th power. Now I can write this as 5c0, and I'm going to go ahead and put in my a to the 5th, plus 5c1, a to the 4th b, plus 5c2, a cubed b squared, plus 5c3, squared b cubed, b cubed, plus, come down here, 5c4, a b to the 4th, plus 5c5, b to the 5th. Now that's putting it in combinatoric form, and rather than go through all that factorial business that we just did, I can use my calculator to find these coefficients for each of the terms, the binomial coefficient for each of these terms. And so we're going to go and just get a refresher. We've used combinatorics on the calculator before, but we're going to refresh ourselves on that a bit. Okay, so we're back over here on the calculator, and we're going to use our combinatoric method here on the calculator to find the coefficients, the binomial coefficients, to expand the binomial a plus b to the fifth. So if I want to get to my combinatorics, I can go to math, and I'm going to scroll over here to probability, and I'm going to choose option 3. Here you see NCR, probability. I'm going to go option 3, and it's going to bring me up to this. Now, if you're on a TI-83, this is a TI-84 plus CE computer emulator. You may see this in parentheses, and you're going to put what I'm getting ready to put in these boxes as with a comma in between, and close your parentheses. So my first was 5, 0, if you remember, 5C, 0. So I got 5. Hit my cursor. It's going to take me over here. I'm going to hit 0. And I'm ready to hit enter. Now again, if you're on a TI-83, you've probably got a parentheses, and you're going to put 5, 0, close your parentheses. And I'm going to hit this, and this is going to equal 1. And it does. Because always remember, if it's n and 0, whatever the n value is, if the r is 0, it's going to equal 1. And at the same time, if it's 5C5, that's also going to equal 1. But I've got to now go to 5C4. No, 5C1, excuse me. So I'm going to hit math and go back over here to probability. Hopefully this won't take too long. I'm going to choose option 3, and I'm going to hit 5. And this time I'm going to hit 1, and I'm going to hit enter. And that binomial coefficient is 5. So what about when it's 5C2? Math, probability, option 3. This time I've got 5C2. And that's going to equal 10. And we're going to do 5C3. So let's go, where am I? Math, probability, option 3. So I got 5C3 also equals 10. Now I got to do 5C4, math, probability. Uh-oh, wrong probability. Let's clear that. Math, probability, option 3. So we got 5C4. Now, because I know that there's a pattern in this, and I've got 1, 5, 10, 10, I bet this is going to equal 5. And it does. I can see that pattern exist. And I don't really have to do 5C5 because I know it's going to equal 1. But just for you, I'm going to do that. Option 3. And I got 5 just to prove it. C5. Enter. And that equals 1. So I then would end up with a to the 5th plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus b to the 5th. And that would expand that binomial that we were working on the previous slide, a plus b raised to the 5th power.